Welcome back, folks. We are still in 5.2, and we just went over some ways to find probabilities for binomial probability distribution situations. So now we're going to expand on that a little bit and look at some batch cases of probabilities. So what do I mean by batch? Well, the title here we got at least, at most, more than, and less than. So these four phrases are ways that we can batch different groups of probabilities together. So the first thing we should do is just make sure you have a full understanding of what these terms mean. Now I'm going to give an example, and we're going to say that n is equal to 10 trials for this example. So now if I wanted to identify what at most 5 is referring to, that is looking at values up to and including 5. So we're going to start at 0 for all of these. And in this case, we're going to start at 0. We're going to go all the way up to 5. So all those individual cases are included and are being referred to for this phrasing. So we do want to include that number, in this case 5. On the other hand, if we're looking at least 5, now we have to flip it around. We're looking at the least value in the list is going to be 5, but then we want everything greater than that. So that's why we want to start at 5 and we want to go up. And we're going to keep going up until we get to n. In this case, n is 10, so that's where we stop. So at least includes the number as well. So those two are similar in that regard, but just be careful which side of the number you're looking at and including. On the other side of, or other hand, I guess, is the other phrasing, which is more than and less than. More than and less than do not include the number. So if you want more than 5, you do not include 5 in that list, going all the way up to n. In this case, it's 10. So we're going to start at 6, 7, 8, 9, and then go up to 10. If we're looking at less than 5, now again, we don't want to include 5 in that list. We want it strictly less than 5. So we're going to start at 0, and then we'll go all the way up to 4. So why is this important? Well, when we're trying to find probabilities that refer to at most and at least and more than and less than, we need to know what individual cases are being described or being referred to. Because if we want to find the overall probability, we just need to look at those individual probabilities and add them together. So in this case here, if I wanted the probability of less than 5, I only need to look at the probability of 0 plus the probability of 1 plus the probability of 2 and 3 and 4. And that's it. Those probabilities combined is equal to the probability that it's less than 5. So that's why it's important. So you got to make sure you really understand what those phrasings mean, and then that's going to help you get these probabilities. So let's take a look at C. 3C is going to say we want n is equal to 9, x is at most 1, p is 0.24. So the first thing we notice is that we're missing q. So let's find q real quick. So 1 minus 0.24, which is 0.76. So now we have all of those pieces, but we still need to break down what at most 1 is. So if x is at most 1, what are those individual cases based on what we just described going to tell us x has to be? If it's at most 1, we want to include 1, but then we want to be everything less than that. So the only thing less than 1 is 0. So now we know the specific cases we need to find, because the probability of at most 1 is equal to probability of 0 plus the probability of 1 based on what we just described. So now we have to go back to the formula, yay, and find those probabilities. So the probability of 0, n is 9 in this case. We're going to have a 9. Then we have our NCR, and then 0 times our p, which is 0.24. And we want to raise that to the 0 power. So again, remember, x matches here. And then we want to probability of Q failure. And then our exponent, remember, is n minus x. So 9 minus 0 is 9. So if we put all of that into the calculator, we will hopefully get our answer. So let's see what we got. So 9 NCR 0 equals 1. Now it's kind of weird, but that's just the way it is. Times 0.24 raised to the 0, which equals 1. So this whole first thing is equal to 1. This whole thing is equal to 1. So really the only thing that contributes to this probability is the 0.76 raised to the 9th, which is that. So 0.08459, blah, 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 blah. So 0.08459, which we will round to 85, 0.085. Okay. One more time. Oops, not equals, but times. And not 0, but 1. Going too fast. Don't go too fast. So again, x is 1, so we want to make sure we have a 1 here. And again, the exponent must match. So, and then 0.76 to the, so again, 9 minus 1, which is 8. So let's see what this one's going to be. So 9 NCR1 equals 9 times 0.24 raised to the first power, which is 0.24. So 0.24 times 9 is this, times 0.76 raised to the 8th equals, so 2404. So if we round it to 3 places, so 240. All right, so now we have those two probabilities. So now we're basically done. We just have to add those probabilities together. And we have our answer. So 0.325 is going to be that probability. So at most 1. The chances of getting at most 1 when n is 9 and the probability of success is 0.24 is 0.325. Now, we're going to look at another one that is similar to this because n is the same, p is the same, which of course means q is the same. But now look at what x is. X is at least 2. Now remember, at least and at most includes that number in the list. So this means that x is equal to what? Do we want the left side, the low side of 2, or the high side? At most, remember, was less than. So we want 2 and up. 4, 5, 6, 7, 8, 9. Wow, that's a lot of individual cases. So we would have to do all those individual cases, use the formula a bunch of times. 1, 2, 3, 4, 5, 6, 7, 8 times. Ugh, I don't want to do that, and you don't want to do that either. Look at the question. How can this be done easier than the above, knowing the requirements for a probability distribution? What do we know about all the probabilities combined in a probability distribution? All those probabilities combined have to add to 1. So if all those probabilities add to 1, and we went through and found all of these individual probabilities, we know we have to add those all up. But if we added what's missing, so in this case, we're missing 0 and 1. Those are the only two numbers we're missing from this list. If we had all of these together, all of these probabilities, they have to add to 1. So if we already have these 2, we can get the rest of these in one lump sum by using the complement rule. So this is what we're going to do. So now the first thing we know is that at least 2 means that we would have to add all of these probabilities up, right? And all the way up to 9. And now, like I said, if I added the probability of 0 and the probability of 1 to this list, that gets me up to a 1 total. But I don't have those 2 in there. So this list is going to be the same, or that sum is going to be the same as if I took 1 and subtracted those 2 that were missing from that list. So that is going to be a lot faster for us because we already know what the answer is from up here. We already know what these 2 probabilities add up to. They add up to 0.325. So if I subtract it from 1, I get 0.675. So that is the answer for this one. This is a lot to process, but the big thing to keep in mind is that you're trying to use that complement rule. All those probabilities have to add up to 1. And if you've already allocated probabilities for these 2, the rest of them have to get you up to 1 when you add them all together. So we're going to see this process again. So if you don't have it quite yet, that's okay. We're going to see it again in upcoming videos. So let's stop there, and then we'll take a look at maybe a different way to find these probabilities. So see you in a minute.